Hello, I'm Umnik. I will be participating in Educational Code First Round 178 and trying to explain what I'm doing. I'm trying the new setup. I mean, it's the same as in the last puzzle video, but I haven't tried it with graphic tablet yet. So we'll see how that goes. There might be some weird things, but hopefully everything will be good. Okay, problem A, 3 decks. The card plays 3 decks of cards in a row on the table. The first deck contains A cards, then B cards and C cards. And A is smaller than B, which is smaller than C. The card wants to take some number of cards, at least one but no more than C, from the third deck and distribute them between the first 2 decks so that each of the taken cards ends up in either the first or the second deck. It is possible that all the cards taken from the third deck will go into the same deck. Tasks to determine whether Mancap can make the number of cards in all 3 decks equal. Okay, so obviously we want so that the sum of numbers is divisible by 3, otherwise it is impossible by any kind of rearrangement. But also A and B should be not greater than that, sum divided by 3, because we can only increase them. If that is true, then we know that C will be strictly greater than the third of all cards. And then we will be able to take what is needed to make A to be equal to the third, what is needed to be to make B equal to the third of all cards, and so the answer will be yes. So we need to check that A plus B plus C is divisible by 3, and B is not greater than the sum divided by 3. And there is some clarification about time limit, but it is for problem G, which we might not even reach. Okay. So we have 3 numbers. I don't actually need the value of C and the value of A. I only care about their sum and value of B. So I need to keep value of B correct, but the sum I can calculate in number C, for example. If C is not divisible by 3, then it's bad. Otherwise we can divide it, and then it is good if and only if B is no greater than C, and I want this function to be bool. Yes, no, yes, no. Is the correct answer. Yes, no, yes, no. I guess for some, usually all of the printfs I hear and then all of the answers, but since I'm mixing scene and printf and printf, I guess it goes weird, but it still should be fine. Problem B. Given an array A consisting of n integers, for every integer k from 1 to n, you have to do the following. Choose an arbitrary element of A and move it to the right end of the array. So we take element somewhere in the middle, or maybe the first one, maybe the last one, some element, and move it to the end. Then print the sum of k last elements of A. Then move the element you have chosen on the first step to its original position. Okay, so we're not doing like an operations, just need to solve some problem for every value of k, and that problem is choose an element, then print the sum of k last elements and restore the array back. You choose the element which you move so that the value you print is the maximum possible. Calculate the value you print for every k. So since the element we choose will be the last one, it will always be calculated. But also like last k minus 1 elements will always be calculated. So I guess we just want to take the sum of last k minus 1 elements plus maximum on the remaining prefix, because we can choose which one we want. Okay, so to do that, we will just like calculate suffix sums and prefix maximums, and then for every value of k, we just take the sum on the suffix, take maximum on the prefix, make their sum, and print the answer. That's kind of like the problem is not worth it. The process is very hard to understand, and like it's not written in the best way. And to solve the problem, you just do exactly what you asked to do. So read the array. I think all the values are positive. So like maximum of empty set is 0. The actual maximums will be bigger, so like this is kind of neutral element. And the suffix sum of empty suffix is also 0. Now we calculate the prefix maximums. And the suffix sums. I'm guessing that the keyboard is well, it's closer to the microphone than me, so it's very loud. Well, don't know if I can do anything about that right now. We need to like understand correctly which suffix and prefix we want like for every value of k, but I think we just like start with empty suffix and the whole array, like on the whole array we take maximum and then go left, so that corresponds to this kind of like downwards for loop. And here we just print pref max plus suffix. Looks good enough. I should also check the limitations. Okay, it's 200,000. I just didn't look at that, so put something that I hoped would be big enough, and it is. Okay, A is accepted. B is running. Problem C, card game. Alice and Bob are playing a game. They have n cards numbered from 1 to n. At the beginning of the game, some of these cards are given to Alice and the rest are given to Bob. Card with number I beats card with number j if and only if I is strictly greater than j, with one exception, card 1 beats card n. So like those kind of rules are common in Russian card game that's called Pianitsa, like at least in my childhood. I think in the English, like the corresponding game is War or something. But I don't know if there is like rules like that. The game continues as long as each player has at least one card. During each turn, the following occurs. Alice chooses one of her cards and places it face up on the table. Bob, seeing Alice's card, chooses one of his cards and places it face up on the table. If Alice's card beats Bob's card, both cards are taken by Alice, otherwise both cards are taken by Bob. Player can use a card that they have taken during one of the previous turns. The player who has no cards at the beginning of turn loses. Determine who will win if both players play optimally. Wouldn't just like the player with card n? Oh no, because one can beat n. Okay. So yeah, if the cards were just in linear order, the player with card n will just always win. If the same player has cards 1 and n, they also win. Because like they can always use card n to take every other card. Yes, the same would be true if the same player has cards n and n-1. Because they could just use n-1 to take all the smaller cards. So we have a player that has card n. If they also have card 1 or card n-1, then they win straight away. So we assume that, so let's say that, okay, our players are not symmetrical, so we cannot say that, like, let's say Alice is the one with card n. So okay, we have a player with card n and another player with cards 1 and n-1. If the player with card n doesn't have any other cards, then that like they will have to play n, and so the other player can just play 1 and win right away. But if the player with card n does have other cards, at least one, and that player is Bob, then Bob wins, right? Because basically for every move of Alice, that move is either one which can be taken by a card that is not n, and every other card can be taken by the card n. Okay, so there is one last case when Alice has card n, probably some other cards, but not 1 and n-1. But then Bob should win, right? Because Bob has 1 and n-1, so 1 can take n, and n-1 can take everything else. So for every move of Alice, Bob can take that card. Okay, so we have like a lot of branching cases, but like all of them are resolved like fast. So it's not like we have like this kind of white tree. We just have like a simple case that is solved, then like all other cases, then another simple case that is solved, and all other cases. So just like a sequence of ifs, and we need to remember about all of them to get this accepted. So we're printing Alice and Bob. Okay, let's say that Alice will be true and Bob will be false. So we will be just returning the answer right away. And we given like n and then string of n characters. Okay. And our string is 0 indexed, so everything I said, like we need to subtract 1 from it. Okay. So if the first character is the same as the last one, or the last two characters are the same, then the person who has the last character will win. And so like it will be Alice if and only if the last character is A. Okay, now Bob can lose if and only if he has the last character, the last card, but not any other card. So like if the last card is in Alice's hand, then Bob wins. Return false. Otherwise, if so we now know that the last card is in Bob's hand. If he has any other card, then he also wins. Otherwise, Alice wins. Sorry about that. Got some delivery, and the boy is very excited about it. Okay, this is hard to check. Alice, then 3 Bobs. Alice, Alice, Bob, Alice. That is the same as here. And we can move on to the next problem. Problem D, array n GCD. You are given an integer array A of size n. You can perform the following operations any number of times, possibly 0. Pay 1 coin and increase any element of the array by 1. You must have at least 1 coin to perform this operation. Gain 1 coin and decrease any element of the array by 1. Okay, so we gain coins by decreasing elements, and then can use that to increase, can use those coins to increase some elements. Well, we don't know what is going to go next, but like the sum of all elements plus the number of coins is constant, right? Because like every time we increase the sum by 1, we pay 1 coin. Every time we decrease the sum by 1, we gain 1 coin. And so like if we don't have any coins at the start, we can only have arrays with not greater sum. Also, like it's interesting if we can make numbers to be like negative or 0, but I guess we'll need to read further to understand that. Let's say that an array is ideal if both of the following conditions hold. Each element of the array is at least 2. For each pair of indices I and j, different, the GCD of I and j is equal to 1, so they're coprime. If the array has less than 2 elements, this condition is automatically satisfied. Well, yes. It's called like vacuously true. If there are no pairs for which the condition can be broken, then like it is true. Let's say that an array is beautiful if it can be transformed into an ideal array using the aforementioned operations, provided that you initially have no coins. Okay, so yeah, we can get any array with sum not greater than the one we start with. Okay, if the array is already ideal, then it is also beautiful. The given array is not necessarily beautiful or ideal. You can remove any elements from it, including removing the entire array or not removing anything at all. It asks us to calculate the minimum number of elements you have to remove, possibly 0, from the array A to make it beautiful. Okay, it seems like pretty simple. I already made some reductions, but like, yeah, you need to like simplify every part of the statement. And then the solution should be pretty simple. So yeah, we already understand that if we start with some array, like basically we are only interested in the number of elements in that array and the sum of those elements. And then we can like build some array with the sum not greater than the sum we had and the same number of elements. Okay, so now how do we make an ideal array? What does it mean to have an ideal array? All the elements must be at least 2, and they are pairwise coprime. That means that for any prime number, there can be only one element of the array that is divisible by that prime number. Otherwise, if we have 2 elements that are divisible by the same prime number, they are not coprime. Their GCD will be divisible by that prime number, so it is not 1, right? So every prime, basically, we can imagine like starting with all 1s and then multiplying some elements by prime numbers, but we can use each prime number at most once. But then like, or at least like, we cannot use the same prime number on different elements. We need to increase every element at least once, because like we start with number 1 and we must get them all to be at least 2, right? And it doesn't make sense to like skip prime numbers or like multiply by the same prime number more than once. So basically our array will be like if we want to have n numbers, we will have n prime numbers, and since we want to have the minimum sum, like to check that it is smaller than our initial sum, we will have just first n prime numbers. Okay, so now the problems that we need to solve, now that we like simplified every step of the statement, now we can look at the problems that we asked to, like the optimization part that we asked to do. We have some numbers, we want to drop some number of them, but like minimum possible number of them, such that after that we can transform that into the ideal array. But transforming into the ideal array, we understand that it is possible if, so let's say that we have k numbers left with sum s, and so like the sum of first k prime numbers must be at most s. Then it should be clear then that like if we know how many numbers we want to have left, then we want the sum to be as big as possible, so we will be dropping the smallest elements we can. So basically we sort our initial array, and then to check if like some value of k, the number of elements we want to keep, is possible, we need to like keep k largest elements and compare their sum to the sum of first k prime numbers. To find prime numbers, we will use some like Eratosthenes sieve. We need to have like 400,000 prime numbers, and like there is a very famous theorem that basically among the first n numbers there are like roughly n divided by log n prime numbers. So like log n on those values is like about 20. So if we have sieved the first 10 million numbers, we will have enough prime numbers. Actually, I think like among the first 10 millions, like somewhere between 500,000 and a million numbers should be prime, and I think it's closer to a million, maybe even bigger than a million. Not sure, but like I'm sure that 10 million is enough, and like the sieve will be fast enough. Like it is possible to do sieve in linear time, but like the simplest way is n log n, and log n is basically nothing. So it will be fine. Okay, we cannot. Well, we can try all the values of k, right? We can sort the array, then like calculate the suffix sums on our array to be able to quickly like calculate the sum of the largest k values, and calculate prefix sums on the sorted array of prime numbers to be able to take the sum of k smallest prime numbers. It can also be shown that you can do some kind of binary search or something, because like, well, imagine that you start with like the whole n numbers left and n prime numbers, and you figure out that okay, the sum is not enough. Then what will happen is we will drop the smallest of our initial numbers and the largest of primes. Maybe the sum is still not enough. We then drop another of our numbers and another prime number, and like each time we do that, the delta to the difference will increase. So basically the function is good. We can do some kind of binary search. But that also shows that like we can just instead of like pre-calculating prefix and suffix sums, we can just maintain the balance. Anyway, like that is the simple part. So the problem solving part was to like understand what that means, and then the rest is easy. And like that is true for many problems. You just like simplify all the parts, and then it's good. So there is also a multitest, but we need to pre-calculate primes. Technically, we can do it for every test separately and like just carefully choose up to which point we will be calculating CIF, but it is much simpler to just do it once before all the tests and just have the array of prime numbers pre-calculated. So how CIF works, we like say that all numbers that are greater than 1 are prime initially, but then we run through the numbers, and if we find the number that is like still prime, it means that it is not divisible by everything smaller than it is actually prime, but then we need to mark all the numbers that are divisible by it as not prime, because they're divisible by this number. So here you can start from x squared, because like all the smaller numbers that are divisible by x should also be marked as not prime, because like they have smaller prime divisor. But like that multiplication needs to be done carefully, like in long clonics, and it is not better by complexity. Like it will still work in like roughly the same time. I guess it's a bit faster, but like it doesn't really matter. And so like I prefer this way because like I don't have to do the casts. Like I can just use ints, and like it shouldn't be much slower. Like I will be surprised if it is like slower at all, like by any noticeable margin. But I also found the prime number, so I want to put it in my array of prime numbers. But I guess like I said that we probably have more prime numbers than we need, and so like if m is equal to big N, we can just break. So all of my numbers are not very big, but their sums are big, so like the balance I will be maintaining is long clock. And yes, I will be calculating like my current sum minus the sum of primes that I need. So it's like this. And I need to like I will start removing the numbers, and I will stop when the balance becomes non-negative. Also, before doing that, I need to sort my array because I want to remove the smallest numbers. I guess I can also reverse. So I start with all the numbers, and while my balance is negative, I decrease the number of elements by 1 and like remove the pair that I'm not using anymore. And now like k is the number of elements that will stay, but I need to print the minimum number of elements I have to remove. So it's n minus k. And I don't need to like put some additional condition here, like when the array becomes empty, so that like I don't go to the like non-existing elements, because all my elements are at least 2, so I'm surely good with just one element, right? So k will never become less than 1 if I'm like doing everything correctly, and I hope that I do. Yeah. Problem E, unpleasant strings. Well, strings are always unpleasant, so that provides 0 information. Let's call a letter allowed if it's a lowercase letter and is one of the first k letters of the Latin alphabet. And k is up to 26. Okay. You're given a string s of length n consisting only of allowed letters. Let's call a string t pleasant if t is a subsequence of s. Given q strings ti, all of them consist only of allowed letters. For each string ti, calculate the minimum number of allowed letters you need to append to it on the right, so it stops being pleasant. So we okay, we're adding some numbers so that the string is not appears as a subsequence. Okay, subsequences are not string problems, so that's fine. Sequence t is a subsequence of sequences if t can be obtained from s by the deletion of several, possibly 0 or all element from arbitrary positions. Okay, that seems pretty simple, and also like must be a known problem or something. Come on, can't be serious. This is long. Okay, let's like assert that I'm actually reached big N, but I'm pretty sure that's true. Oh, I need to run up to big M here. That is a bug, unfortunately. Okay, so how do we check if one string is a subsequence of another? Well, it's done greedily. We will just try to find the corresponding subsequence, and how we will find it? Just by running from left to right. Like, and we run from left to right by the like string that we want to check to be a subsequence, but also we will move through the big string, and when like for every character of our like smaller string, we want to find the first occurrence of that character that is to the right of everything that we previously found. So basically, if we like want to find like this BCB, we'll say, okay, let's run left to right, and so A is not good, then B is good, because like we want this B. So now we will want a C, which is to the right of this B. So in this case, we just taken all the letters B, C, and B, but like if there was a C at the start, that wouldn't change anything. Like we first we want to find the first character, then like starting from that point, the second character, and the third one, and so on. Now let's say that, okay, we did it for our given string, and we found it. Then we can we are allowed to append characters, to add more characters. So basically we will say, okay, now we are searching for the next character that we can choose. So first characters are given to us, but then we can choose each one. How we will choose it? Well, we want that character, ideally we want to not have it on the suffix, right? So that we just stop there. We add that character, and hooray, it is not a subsequence anymore. But if all the characters are present there, then we will want to take the character that appears first from that position, as right as possible. So the last character that we see from that position, because that will move us further in the string. And so our choice depends only on where we were standing in the string. So if we were standing at some position, we want to choose the character that appears last on that suffix. And so we can basically remember for every position what jump we will do. And we don't want to do those jumps actually for every query, because that would be slow. If we just do it naively, we might have to jump through the whole string, right, for every query, and that would be n times q. But we can just pre-calculate the answer for every position, right? So for every position, we know where we jump, and we know the answer. Basically, we're calculating dp from the end of the string. So if we have reached the end, then just putting any character will be good. Then we move back, find the jump we will do, and look at the answer there and add 1 to that. And we will also pre-calculate for every position, we'll pre-calculate where the next letter is for each letter. So we will have this big matrix of size n times k, but that is fine, we have a lot of memory. And we will also use it to process queries faster, because we don't want to run through the string each time. We want to just jump to the next occurrence of the character we want, so that that way we will process each query in time proportional to the size of that string, not the big string but the query string, because for every character we will just do one jump that is pre-calculated. And our working time will be n times k plus the sum of lengths of all the query strings, which is bounded by 10 to the 6. Okay, fix the bug. Now I can implement problem E. K, then the string, then Q, then all the queries. This will be our array nxt for each position, where is the next occurrence of each letter. write to that position. And we will also have array dp for every position. If we stay in here, how many more letters we need to like go out of the string. If we're already like after the last character, then we do not have any more characters to the right, and we will say that the next occurrence, like we will do the jump to the position n+1, which is like dummy position. That means that we are done. Now we will run from right to left and precalculate all the matrix next. So how to do that? When we are looking for character C, either it is the next one, or we will have to jump to the same point where we would jump if we started like one more to the right. So we will first copy like the next column of our table, and then say, okay, for one character that is si, we will jump to i+1 just after that character. Okay, great. Now we have array nxt. Now for every position in our string, again from right to left, we will calculate dp. To calculate dp, we will choose the character that is for which like nxt is the first one, and then take dp value there +1. Or we can just like calculate maximum of dp values at start, because they will be increasing from right to left. So it is the same, but I don't need to create a new variable for like what is the best character. So I took the maximum of dp's and then I increased by 1. And now we will just answer the queries. So we are staying at some position, and for every character that we have, we jump to the like after the next occurrence of that character. And I added this condition because like if I'm jumping out of the string, I don't have values next calculated for them. I could just fill them with n+1. Basically, if we are already out of the string, then for every next character we still be out of the string. Or I can add this condition. It's the same. And then the answer is just calculated in dp of p. okay, I want minimum here, but that means that I need to initialize with something. Okay, that's better. Problem F, numbers and strings. For each integer x from 1 to n, we will form the string s of x according to the following rules. Compute x plus 1, write x and x plus 1 next to each other in the decimal system without separators and leading zeros. In the resulting string, sort all digits in non-decreasing order. Okay, we have some examples. Your task is to count the number of distinct strings among S1, S2, and so on Sn. N is up to 10 to the 9th minus 2, because like for n we will take n plus 1 and we wanted to have less than n characters. Okay, sure. And I have 10 to the 4th test cases, which like kind of important here, I think. But maybe, yeah, probably I can solve like all the test cases at the same time. Okay, so each of the strings s of x is a string of digits that is non-decreasing of length at most 18, right? Like the largest number we can have has length 9, and then x plus 1 will also have length 9, so we'll have like 18 digits here. How many strings are there which consist of digits of length no more than 18 and that are non-decreasing? Not that many, it turns out. Let's say that we fix like length to be exactly 18, right? Then how can we represent those strings? Basically, we have like 18 numbers, but we also have some places like when we basically we start from zeros, so we will have some number of zeros, then we will have some number of ones, maybe 0, some number of twos and threes, and so on. So let's say that we will construct our number as follows. Like we start with number current number 0, and we will like go left to right, and we can either place the current number on the current position and move to the next position, or we can increase our current number. And so when we reach the like number 10, we cannot place any more numbers. That means that our strings have like a bijection with sequences of operations where each operation is either place the current number or increase the current number by 1. And the number of placements is at most 18. The number of increases is 10. And like after the last increase, we stop. But we can just say that, okay, let's say that we have always 18 places, just we ignore the places that will be after the last, we ignore the places that we will have after the last increase. So that number is the same as the number of ways to arrange 18 operations place and 10 operations increase. And we will also count an empty string, whatever. So that number is binomial coefficient choose 10 from 28, and it is not that big. Right? Sum of binomial coefficients from 28 is 2 to the power of 28. The 10th binomial coefficient is not the middle one, but it is pretty close to the middle one. So it probably should be like something probably something like 10 to the 28 divided by 20 or something. You can count it, like you can use Google or just write a simple code that will calculate the binomial coefficient. But like I'm estimating that it is like 10 to the 7th multiplied by something like not very big. 3 maybe, like maybe 2, 3, something like that. So I can build all of those strings. Then for every such string, I want to check if it appears among those, but I don't know n. Like I cannot do that for every test. I have to do it once. But like what I actually want is to find the smallest number x for which s of x will be the string I'm talking about. Why is that? Well, because basically if I increase n, I'm adding new strings, and I want to find the first time that string will be added. So I will find all of those numbers x, or like I will figure out that that string cannot be constructed in this way. I think most of them will be like that. And if I understand like for every string quickly enough, I should be able to just find all of those numbers, and then the answer to the query will be basically how many numbers not greater than n I have in my list. To solve that, I will just sort that list, and then the query is just like upper bound in that list. Basically, upper position of the upper bound is the answer to the query. So that's the plan. Now I just need to implement that plan. So how do I check if the given string is good? Okay, so we have like x and x plus 1. X and x plus 1 should be pretty similar, right? If we write x in decimal, we then add 1. How do we add 1? We start from the lowest positions, and while they are 9s, we are replacing them by zeros. But when it's not 9, we just increase the digit and then stop. And so basically I want like for my, basically I have a multi-set of numbers I can rearrange. So I can like remove some equal number of nines and zeros by saying that like that's the number of nines I will have, and then I have to remove some digit, and then that digit plus one, and the digit must be not nine. Um, okay, so it's probably easier to just hard code the case when we have like all nines, because it will be like all nines, but we don't have the zero before the nine, and we will have like all nines and then one and a lot of zeros. But that can only happen if the length of my string is odd. So if the length of the string is odd, I just check that that's the case. If yes, then I know what the number is. Otherwise, I do not have that situation. And then uh, let's say that I have like digit C and then K nines, then I will have like C plus one and K zeros. But one of the C and C plus one is not a zero or a nine. And so that number, that digit will have like exactly one more than like exactly one more in the part that is changing, and so it will have odd number of appearances. And I can look for the digit with no odd number of appearances. I guess there still will be some cases. Uh, okay, like among the digits that are not 0 and 9, uh, there must be at least one digit with odd number of appearances, but not more than two. If there are two of them, they should be next to each other, and that like C and C plus one. If uh, if there's just one of them, it must be either a 1 and then C was 0 and C plus 1 was 1. And then that's why it's odd. Or it was an 8 and then C is 8 and C plus 1 is 9. So in any case, I know the value of C. Now I need to choose how many nines I need to make like after it. And like after, so I have like C plus 1. Those two parts must be the same, and those must be like some number of nines and the same number of zeros. If I choose the number of nines and zeros, like the suffix I want to make like the smallest number that is possible to make, which is like more or less just sorting all the digits in increasing order, except I cannot start with 0. So, how do I choose how many zeros and nines I want? I probably want the least possible number of them. Like I know the parity, so maybe I have to do it once to make number of zeros and nines to be even, so that I can use them in the first part. But then, if I have some zeros left, I want to have them. Because like basically I can choose to remove 1 0 and 1 9 from the first part. But that's always bad because like I will be picking a 0 out of a number that will increase it. Like it stays in the same place, so it will be shifted like left to the higher digits. So I will pick a 0 and then a 9, and like that 0 will be replaced by some non-zero number, which is like always bad. Except, oh my god, except maybe in the case when I don't have any numbers after it. No, it still should be better to not remove them, except in the case when I don't have any other digits. Yeah, if I don't have any digits other than zeros and nines, then maybe, well, not maybe, like certainly, I want to remove all of them. Because my digit C is not 9. And if I only have zeros and nines, I will have to put a 9 on the first place. And if I remove all of them, then I will have a smaller digit in the first place. But that like can only be done if can remove all of them. Yeah, this is not great. Okay, well, it is the way to solve it, and I guess like those will be the corner cases. Like those numbers do exist. Like if I take the number like 3999 then as x, then s of x will be like my set of numbers set of digits will be 39994000. So I will understand that 3 and 4 are my like C and C plus 1, and then I have 3 nines and 3 zeros. I have to move one of them. And like if I don't move the rest, my number will be like 9039 and like plus 1 9040. and it will have correct set of digits afterwards. But if I move both of them, then I will get 3999, and it is a smaller number, so I need to get that one. Okay, so I will just have to just write those ifs and deal with those corner cases. And I don't think there is a way around that. I will need some array where I just like put all the numbers I construct. I know that its length is not like super big. I also think that it is not big at all. So I think it's like smaller than a million, and maybe even smaller than that. But like for now, let's put like 10 million. That's too much. And like after I write the solution, we will see how many numbers are there. Okay, so in the CNT, I will count the number of zeros, ones, twos, and so forth I'm constructing. So yeah, basically I will be constructing them as like as a multi-set, not as a string. So I'm just calling brute force. My current digit is 0. The number of digits I placed is also 0. I do not want to place more than 18 digits. The rest of the solution is super easy, but like, let's first focus on writing the brute force and then checking function. So that's my current digit and my current length. So if the digit has reached 10, I should check if that multi-set of digits is good, and if it is, find the smallest number of number x that it corresponds to and put it in the answer. So I will just call the function check, give it length, and then return. If length has reached 18, then I don't want to increase it further, and I can also just run check from length and return. Otherwise, both options are available. I can either increase the current digit or put the current digit in my multiset one more time. So the first option is to just increase the digit. The other option is to say that I'm taking it, so calling brute force is length plus 1, but then removing it back. So like all like now it's super easy to see like that it should be like binomial coefficient. I'm just considering like two options, but I'm breaking when I have too many. I have something else, sorry. And that wasn't even for me. Cannot protect from that. Right, what was I saying? Yeah, that I'm just choosing one of two options, but stopping when like I reached the limit on one of them. Okay, so now I need to write the function check. If length is smaller than 2, that's bad. If length is odd, that's a very specific case. We know that it should be like a lot of 9s, and after adding 1, it should be like 1 and a lot of 0s. So we just check that we have exactly length divided by 2 zeros and the same number of 9s and exactly 1. If all of that is true, then our number is like len over 2 9s. So let's just get it. So that's our number, and we just put it in uns. And then return. So if it was a good number, then we put it in uns and then return. If it wasn't, then just return. It's a bad string. Don't need to do anything. Okay, now I want to figure out. I think I want to have this copied because like I'm using it in brute force, and I think I want to like decrease the counts. Okay, so now I want to figure out what my digit C is. For that, I will look at the parities of C and T. For digits that are not 0 or 9, and look at them. I also could have like maintained it in brute force, and if I have more than 2 digits with odd number of occurrences that are not 0 or 9, I could just like stop the brute force. I know that all those strings are invalid. If I needed to speed it up, I would do it. We'll see if I need it, but I think it should be fast enough as it is. But we'll see. Okay, so let's just say that we start with digit 1 and while c is smaller than 9 and c of c mod 2 is 0, C++. If I didn't find anything, that's just bad. If I stopped right away, C is 1. Maybe it is not 1 actually. Like if C is 1, else if C is 8, else no case. So if C is 1, then if digit 2 appears odd number of times, then C was actually 1. Otherwise, it was 0. So if C of 2 mod 2 is 0, then I actually want to check 0. Okay, yeah, actually that's fine for now. So I'm saying that like my digit is C. The next, so C plus 1 is the digit that I will have in X plus 1. And so I need to check that for all the digits after that, they are all even. Up to 9. If C of I and 1, just return, because that means that my string is absolutely bad. Okay, now C is the only possible value for that digit, and if CC of C is 0, that's also bad, because I need to use it. C of C is 0, or if C of C plus 1 is 0, it's bad. Otherwise, I'm saying, okay, I'm taking them. Okay, I took them. Now the counts for all the digits except 0 and 9 must be even. For 0 and 9 though, they might be odd. So now we need to choose the number of 9s. We start with 0. If I have odd number of zeros, I also must have odd number of 9s. And so I'm just taking 1 for now. Okay, I took 1. Great. Now, like in almost all the cases, I do not want to take more than that. except yeah, if except like my C and C++, all other digits are zeros and nines, then I want to take all of them. All other digits are zeros and nines, and I have equal number of them. Then I want to take all of them, except when C is 0. Oh my god. I guess that case also exists, right? Like if I have 990 and 991, like that's a valid pairing. No, not that. 900 and 901. I would love to take those nines and zeros and move them to the right and get 099100. That would be smaller, but it would be incorrect because I have a leading zero. Okay. So okay, after I do this, if C is not 0 and C of 0 is ln over 2 minus 1 and C of 9 is ln over 2 minus 1, yeah, then it is better to just put C and then all of the nines, and then I will have C plus 1 and all of the zeros, and that is optimal. And so my number will be like C plus 1 times 10 to the power of like how many zeros I have, minus 1, because like, that's all the nines. Okay, now I don't want more nines. Great. And so now I have C, C plus 1, maybe 90 at the end. But all other digits, I just want to sort, except the first one must be non-zero. So I want to find non-zero digit that I have. So while I don't have them, f plus plus, and while f is smaller than 10, if f is 10, then like all my digits are zeros and I just cannot do anything about it. Except maybe Like if I don't have any more digits, but I think it should be covered by this case. Yeah, like apart from C and C+1, I only had 9s and 0s, and they were equal number of them, so that should be covered by this case. Okay, great. So it's just bad. Otherwise, I'm taking that number, that digit, then I took two occurrences of that digit because I'm placing like the same number. Now I will run through all the digits that like in the left part. The number of times I'm taking them is this. Like that's the number of occurrences of the digit I have, but to take it, like I'm using two occurrences because I'm placing it in x and x plus 1. And I'm placing like that next digit that transforms my number to 10 times x plus that digit. Then I'm placing digit c, and then if 9s, or like I guess put that number of 9s, but it is always 0 or 1 in my case. That's it. Just below 10 to the 6, and it works like immediately. I don't know if it works correctly, but we'll see. And so now like all the tests are just queries to that, and the query is pretty simple. I need to sort my answer array. And the answer is just upper bound ans plus size x minus ans. What? Yeah, it won't be easy to debug because like it's kind of specific. Okay, I mean I can decrease this number. But it still will be like a lot to sift through. Okay, so those will be all the things I'm checking. Yeah, there will be a lot of them. Okay, let's try to set this to 4 first. There will be some reasonable number of them. That's not right, is it? 7, 8. Yeah. So here. Okay, let's just make it simpler. I'll move this higher. We need to do this surely, and now I can just check for all the digits other than 0 and 9 that I have even number of them. Yeah, that looks more reasonable. Okay, let's see if it works. What do you mean? Oh, great. Can just do that. Yeah, that looks like a correct answer, but I need 18 here. And yeah, the number got a bit smaller, but still like close to 1 million. Okay. Can try to submit that. It's interesting to notice that like usually in such kind of problem they will just give in the sample something big, right? Like, why not? And well, the reason why not is that the answer for that number is pretty small, like smaller than 1 million, and that would give the idea that, oh, maybe I can generate all the different strings. Yay, accepted. Phew. Yeah, that was a bit brutal. We have 20 more minutes and it's some queries problem, but okay, modulo 3. Surely you have seen problems which require you to output the answer modulo 10 to the n plus 7. Okay, but have you ever seen a problem where you have to print the answer modulo 3? It's a good question. I'm sure I have seen the problems where I need to print the answer modulo 2 and modulo 4. Modulo 3? Don't know. You are given a functional graph consisting of n vertices numbered from 1 to n. It is a directed graph in which each vertex has exactly one outgoing arc. The graph is given as the array G1, G2, and so on, where Gi means that there is an arc that goes from I to Gi. For some vertices, the outgoing arcs might be self-loops. Okay. Initially, all the vertices of the graph are colored in color 1. You can perform the following operation. Select a vertex and a color from 1 to k, and then color this vertex and all the vertices that are reachable from it. You can perform this operation any number of times, even 0. Okay, you should process q queries. The query is described by 3 integers x, y, and k. For each query, you should assign g of x to be equal to y, then calculate the number of different graph colorings for the given value of k. Two colorings are different if there exists at least one vertex that is colored in different colors in these two colorings. Since the answer can be very large, print it modulo 3. Note that in every query, the initial coloring of the graph is reset. All vertices initially have color 1 in each query. Okay. That actually seems like a problem that might be able to solve in 20 minutes. Okay, so the functional graphs, they look like this collection of what we call suns. So a sun is a cycle, but there are also some trees growing from some vertices on the cycle. Something like that. And we can have like several such suns. Okay, each time we like do the coloring action, like let's say we do the coloring in this vertex, then what we will reach is the vertical path to the, like in the tree plus all the vertices in the cycle. So I think that we can choose like any colors for all the three vertices. Why is that? That's because basically if we fix a coloring that we want to achieve, we just need to go from the leaves, and for the leaf like we can apply the coloring in it, and like it will change the color in the leaf to the correct one. It will also change all the higher colors, but we do not fix them yet. And so like we do all of that. And then for the cycle, we also choose the color, but the color should be the same for all the vertices in the cycle. So basically, the cycle is counted as one vertex, and then the number of colorings is just like k to the power of like this changed number of vertices. Like m is number of vertices if each cycle is counted as one vertex. Okay. Now we want to calculate this modulo 3. So if k is 0 modulo 3, then this is 0 modulo 3. If k is 1 modulo 3, then this is 1 modulo 3. If k is 2, then it means that it is like -1. to the power of m modulo 3. So actually we need to calculate number m modulo 2 to be able to answer this query. So the parity of m should be like the parity of n XOR the parity of the number of cycles XOR the parity of total length of all the cycles. But how do I maintain that? Well, I guess it should be like technically possible to like maintain everything with some like insane data structures, like some linked cactus or whatever. But I'm assuming that they're asking for parity because it is easier to calculate. But like, even if I was guaranteed that like the graph is a permutation, like when I'm asked, so I can make like several changes, and then like it is guaranteed that it is a permutation now. Like say the parity of the number of cycles. I don't know how to do that fast. Like how solvable it is. Because problem F is probably pretty hard. Okay, so it's on level with F. Maybe it would even have more if like they were swapped. Maybe we can do some kind of square on queries. Like split the queries into square blocks of some size, like square. Now inside of the block, like, some edges will change, but most of them will not. So we can like compress something. We can like find all the cycles that we already have, and everything else will be like rooted trees, where from root we do not have an edge yet. And then for the edges, like for each query, then like we add those square edges and figure out like what are the cycles. And like what are we going to do with them? Yeah, that seems doable. Like, and I don't think that there are even any like logarithms. Just square. Also, like again, I don't see why it is important that I'm doing it modulo 2. I can just find that number m, and like, I would be able to print k to the power of m any modulo. Probably you can use it somehow, that you only need the parity. But I don't see how. And like, surely I cannot implement it in 7 minutes. Weird problem. Maybe there is something interesting, I'm just not seeing it. Okay, thanks for watching. Bye.